Liquefied natural gas is natural gas that has been converted to liquid form for ease of storage or transport. It takes up about 1/600th the volume of natural gas in the gaseous state. It is odorless, colorless, non-toxic and non-corrosive. Hazards include flammability after vaporization into a gaseous state, freezing and asphyxia. The liquefaction process involves removal of certain components, such as dust, acid gases, helium, water, and heavy hydrocarbons, which could cause difficulty downstream. The natural gas is then condensed into a liquid at close to atmospheric pressure by cooling it to approximately 162 degrees Celsius. Maximum transport pressure is set at around 25 kPa. LNG achieves a higher reduction in volume than compressed natural gas so that the energy density of LNG is 2.4 times greater than that of CNG or 60% of that of diesel fuel. This makes LNG cost-efficient to transport over long distances where pipelines do not exist. Specially designed cryogenic sea vessels or cryogenic road tankers are used for its transport. LNG is principally used for transporting natural gas to markets, where it is regasified and distributed as pipeline natural gas. It can be used in natural gas vehicles, although it is more common to design vehicles to use compressed natural gas. Its relatively high cost of production and the need to store it in expensive cryogenic tanks have hindered widespread commercial use. Energy density and other physical properties. The heating value depends on the source of gas that is used and the process that is used to liquefy the gas. The range of heating value can span +/10 to 15%. A typical value of the higher heating value of LNG is approximately 50 megajoule per kilogram or 21,500 a British thermal unit per pound. A typical value of the lower heating value of LNG is 45 megajoule per kilogram or 19,350 a British thermal unit per pound. For the purpose of comparison of different fuels, the heating value may be expressed in terms of energy per volume, which is known as the energy density expressed in megajoule per liter. The density of LNG is roughly 0.41 a kilogram per liter to 0.5 a kilogram per liter, depending on temperature, pressure, and composition, compared to water at 1.0 a kilogram per liter. Using the median value of 0.45 a kilogram per liter, the typical energy density values are 22.5 megajoules per liter or 20.3 megajoules per liter. The energy density of LNG is approximately 2.4 times greater than that of CNG, which makes it economical to transport natural gas by ship in the form of LNG. The energy density of LNG is comparable to propane and ethanol but is only 60% that of diesel and 70% that of gasoline. History. Experiments on the properties of gases started early in the 17th century. By the middle of the 17th century, Robert Boyle had derived the inverse relationship between the pressure and the volume of gases. About the same time, Guillaume Montan started looking into temperature effects on gas. Various gas experiments continued for the next 200 years. During that time there were efforts to liquefy gases. Many new facts on the nature of gases had been discovered. For example, early in the 19th century Cagniard de Latours had shown there was a temperature above which a gas could not be liquefied. There was a major push in the mid to late 19th century to liquefy all gases. A number of scientists including Michael Faraday, James Joule, and William Thomson, did experiments in this area. In 1886 Karol Olszewski liquefied methane, the primary constituent of natural gas. By 1900 all gases had been liquefied except helium, which was liquefied in 1908. The first large-scale liquefaction of natural gas in this country was in 1918 when the U.S. government liquefied natural gas as a way to extract helium, which is a small component of some natural gas. This helium was intended for use in British dirigibles for World War I. The liquid natural gas was not stored, but regasified and immediately put into the gas mains. The key patents having to do with natural gas liquefaction were in 1915 and the mid-1930s. In 1915 Godfrey Cabot patented a method for storing liquid gases at very low temperatures. It consisted of a thermos bottle-type design which included a cold inner tank within an outer tank. the tanks being separated by insulation. In 1937 Lee Twomey received patents for a process for large-scale liquefaction of natural gas. The intention was to store natural gas as a liquid so it could be used for shaving peak energy loads during cold snaps. Because of large volumes it is not practical to store natural gas, as a gas, near atmospheric pressure. However, if it can be liquefied it can be stored in a volume 600 times smaller. This is a practical way to store it, but the gas must be stored at -260 degree Fahrenheit. There are basically two processes for liquefying natural gas in large quantities. One is a cascade process in which the natural gas is cooled by another gas which in turn has been cooled by still another gas, hence a cascade. There are usually two cascade cycles prior to the liquid natural gas cycle. The other method is the line process. In this process the gas is cooled regeneratively by continually passing it through an orifice until it is cooled to temperatures at which it liquefies. The cooling of gas by expanding it through an orifice was developed by James Joule and William Thomson and is known as the Joule-Thomson effect. Lee Twomey used the cascade process for his patents. The East Ohio Gas Company built a full-scale commercial liquid natural gas plant in Cleveland, Ohio, in 1940 just after a successful pilot plant built by its sister company, Hope Natural Gas Company of West Virginia. This was the first such plant in the world. Originally it had 3 spheres, approximately 63 feet in diameter containing LNG at -260 degree Fahrenheit. Each sphere held the equivalent of about 50 million cubic feet of natural gas. A fourth tank, a cylinder, was added in 1942. It had an equivalent capacity of 100 million cubic feet of gas. The plant operated successfully for 3 years. The stored gas was regasified and put into the mains when cold snaps hit and extra capacity was needed. This precluded the denial of gas to some customers during a cold snap. The plant failed on October 20, 1944 when the cylindrical tank ruptured, spilling thousands of gallons of LNG over the plant and nearby neighborhood. The gas evaporated and caught fire, which caused 130 fatalities. The fire delayed further implementation of LNG facilities for several years. However, over the next 15 years new research on low-temperature alloys, and better insulation materials, set the stage for a revival of the industry. It restarted in 1959 when a U.S. World War II Liberty ship, the Methane Pioneer, converted to carry LNG, made a delivery of LNG from the U.S. Gulf Coast to energy-starved Great Britain. In June 1964, the world's first purpose-built LNG carrier, the Methane Princess, entered service. Soon after that a large natural gas field was discovered in Algeria. International trade in LNG quickly followed as LNG was shipped to France and Great Britain from the Algerian fields. One more important attribute of LNG had now been exploited. Once natural gas was liquefied it could not only be stored more easily, but it could be transported. Thus energy could now be shipped over the oceans via LNG the same way it was shipped by oil. The domestic LNG industry restarted in 1965 when a series of new plants were built in the U.S. The building continued through the 1970s. These plants were not only used for peak shaving, as in Cleveland, but also for base load supplies for places that never had natural gas prior to this. A number of import facilities were built on the East Coast in anticipation of the need to import energy via LNG. However, a recent boom in U.S. natural production, enabled by the new hydraulic fracturing technique, has many of these import facilities being considered as export facilities. The U.S. Energy Information Administration predicts, with present knowledge, that the U.S. will become an LNG exporting country in the next few years. Production: the natural gas fed into the LNG plant will be treated to remove water, hydrogen sulfide, carbon dioxide and other components that will freeze under the low temperatures needed for storage or be destructive to the liquefaction facility. LNG typically contains more than 90% methane. It also contains small amounts of ethane, propane, butane, some heavier alkanes, and nitrogen. The purification process can be designed to give almost 100% methane. One of the risks of LNG is a rapid phase transition explosion, which occurs when cold LNG comes into contact with water. The most important infrastructure needed for LNG production and transportation is an LNG plant consisting of one or more LNG trains, each of which is an independent unit for gas liquefaction. The largest LNG train now in operation is in Qatar. These facilities recently reached a safety milestone, completing 12 years of operations on its offshore facilities without a lost time incident. Until recently it was the Trainer 4 of Atlantic LNG in Trinidad and Tobago with a production capacity of 5.2 million metric ton per annum, followed by the SEGAS LNG plant in Egypt with a capacity of 5 LMTPA. In July 2014, Atlantic LNG celebrated its 3,000th cargo of LNG at the Campania Euro unregistered trademark S liquefaction facility in Trinidad. The Qatar 2 plant has a production capacity of 7.8 MMTPA for each of its two trains. LNG sourced from Qatar 2 will be supplied to Kuwait, following the signing of an agreement in May 2014 between Qatar Liquefied Gas Company and Kuwait Petroleum Corporation. LNG is loaded onto ships and delivered to a regasification terminal, where the LNG is allowed to expand and reconvert into gas. Regasification terminals are usually connected to a storage and pipeline distribution network to distribute natural gas to local distribution companies or independent power plants. LNG plant production information for the following table is derived in part from publication by the U.S. Energy Information Administration. Equatorial Guinea 2007 3.4 Marathon oil, world total production. The LNG industry developed slowly during the second half of the last century because most LNG plants are located in remote areas not served by pipelines, and because of the large costs to treat and transport LNG. Constructing an LNG plant costs at least $1.5 billion per 1 MMTPA capacity. A receiving terminal costs $1 billion per 1 BCF day throughput capacity and LNG vessels cost $200 million €, $300 million. In the early 2000s, prices for constructing LNG plants, receiving terminals and vessels fell as new technologies emerged and more players invested in liquefaction and regasification. This tended to make LNG more competitive as a means of energy distribution, but increasing material costs and demand for construction contractors have put upward pressure on prices in the last few years. The standard price for a 125,000 cubic meter LNG vessel built in European and Japanese shipyards used to be $250 a million. When Korean and Chinese shipyards entered the race, increased competition reduced profit margins and improved efficiency, reducing costs by 60%. Costs in US dollars also declined due to the devaluation of the currencies of the world's largest shipbuilders, the Japanese yen and Korean won. Since 2004, the large number of orders increased demand for shipyard slots, raising their price and increasing ship costs. The per ton construction cost of an LNG liquefaction plant fell steadily from the 1970s through the 1990s. The cost reduced by approximately 35%. However, recently the cost of building liquefaction and regasification terminals doubled due to increased cost of materials and a shortage of skilled labor, professional engineers, designers, managers and other white-collar professionals. Due to energy shortage concerns, many new LNG terminals are being contemplated in the United States. Concerns about the safety of such facilities created controversy in some regions where they were proposed. One such location is in the Long Island Sound between Connecticut and Long Island. Broadwater Energy, an effort of TransCanada Corporation and Shell, wishes to build an LNG terminal in the Sound on the New York side. Local politicians including the Suffolk County executive raised questions about the terminal. In 2005, New York Senators Chuck Schumer and Hillary Clinton also announced their opposition to the project. Several terminal proposals along the coast of Maine were also met with high levels of resistance and questions. On September 13, the U.S. Department of Energy approved Dominion Cove Point's application to export up to 770 million cubic feet per day of LNG to countries that do not have a free trade agreement with the U.S. In May 2014, the FERC concluded its environmental assessment of the Cove Point LNG project, which found that the proposed natural gas export project could be built and operated safely. Another LNG terminal is currently proposed for Elbe Island, GA. Plans for 3 LNG export terminals in the U.S. Gulf Coast region have also received conditional federal approval. In Canada, an LNG export terminal is under construction near Guysborough, Nova Scotia. Commercial aspects, global trade. In the commercial development of an LNG value chain, LNG suppliers first confirm sales to the downstream buyers and then sign long-term contracts with strict terms and structures for gas pricing. Only when the customers are confirmed and the development of a Greenfield project deemed economically feasible, could the sponsors of an LNG project invest in their development and operation. Thus, the LNG liquefaction business has been limited to players with strong financial and political resources. Major international oil companies such as ExxonMobil, Royal Dutch Shell, BP, BG Group, Chevron, and national oil companies such as Petamina and Petronas are active players. LNG is shipped around the world in specially constructed sea-going vessels. The trade of LNG is completed by signing an SPA between a supplier and receiving terminal, and by signing a GSA between a receiving terminal and end users. Most of the contract terms used to be DES or ex-ship, holding the seller responsible for the transport of the gas. With low shipbuilding costs, and the buyers preferring to ensure reliable and stable supply, however, contract with the term of FOB increased. Under such term, the buyer, who often owns a vessel or signs a long-term charter agreement with independent carriers, is responsible for the transport. LNG purchasing agreements used to be for a long term with relatively little flexibility both in price and volume. If the annual contract quantity is confirmed, the buyer is obliged to take and pay for the product, or pay for it even if not taken, in what is referred to as the obligation of take-or-pay contract. In the mid-1990s, LNG was a buyer's market. At the request of buyers, the SPAs began to adopt some flexibilities on volume and price. The buyers had more upward and downward flexibilities in TOP, and short-term SPAs less than 16 years came into effect. At the same time, alternative destinations for cargo and arbitrage were also allowed. By the turn of the 21st century, the market was again in favor of sellers. However, sellers have become more sophisticated and are now proposing sharing of arbitrage opportunities and moving away from S-curve pricing. There has been much discussion regarding the creation of an OGEC as a natural gas equivalent of OPEC. Russia and Qatar, countries with the largest and the third largest natural gas reserves in the world, have finally supported such move. Until 2003, LNG prices have closely followed oil prices. Since then, LNG prices in Europe and Japan have been lower than oil prices, although the link between LNG and oil is still strong. In contrast, prices in the US and the UK have recently skyrocketed, then fallen as a result of changes in supply and storage. In late 1990s and in early 2000s, the market shifted for buyers, but since 2003 and 2004, it has been a strong seller's market, with netback as the best estimation for prices. Research from QNB Group in 2014 shows that robust global demand is likely to keep LNG prices high for at least the next few years. The current surge in unconventional oil and gas in the U.S. has resulted in lower gas prices in the U.S. This has led to discussions in Asia oil-linked gas markets to import gas based on Henry Hub Index. Recent high-level conference in Vancouver, the Pacific Energy Summit 2013 Pacific Energy Summit 2013 convened policy makers and experts from Asia and the U.S. to discuss LNG trade relations between these regions. Receiving terminals exist in about 18 countries, including India, Japan, Korea, Taiwan, China, Greece, Belgium, Spain, Italy, France, the UK, the US, Chile, and the Dominican Republic, among others. Plans exist for Argentina, Brazil, Uruguay, Canada, Ukraine and others to also construct new receiving terminals. Use of LNG to fuel large over-the-road trucks, In the United States, the beginnings of a public LNG fueling capability is being put in place. An alternative fueling center tracking site shows 56 public LNG fuel centers as of July 2014. As of July 2014, Blue LNG has at least 15 operational LNG-capable fuel centers across 8 states. In May 2013, Dillon Transport announced they were putting 25 LNG large trucks into service in Dallas, Texas. They are refueling at a public LNG fuel center. In the spring of 2014, Shell and Travel Centers of America opened the first of a planned network of U.S. truck stop LNG stations in Ontario, California. UPS is planning to have over 900 LNG-fueled trucks on the roads by the end of 2014. Clean Energy Fuels has opened several public LNG fuel lanes and claims that as of June 2014, LNG-fueled trucks can use the route from Los Angeles, California to Houston, Texas on I-10 by refueling exclusively at Clean Energy Fuels public facilities. Clean Energy maintains a list of their existing and planned LNG fuel centers. As of July 2014, they had 30 operational public LNG facilities. In fall 2013, Lowe's finished converting one of its dedicated fleets to LNG-fueled trucks. Trade. In 1970, global LNG trade was of 3 billion cubic meters. In 2011, it was 331 BCM. In 2004, LNG accounted for 7% of the world unregistered trademark as natural gas demand. The global trade in LNG, which has increased at a rate of 7.4% per year over the decade from 1995 to 2005, is expected to continue to grow substantially. LNG trade is expected to increase at 6.7% per year from 2005 to 2020. Until the mid-1990s, LNG demand was heavily concentrated in Northeast Asia, Japan, Korea and Taiwan. At the same time, Pacific Basin supplies dominated world LNG trade. The worldwide interest in using natural gas-fired combined cycle generating units for electric power generation, coupled with the inability of North American and North Sea natural gas supplies to meet the growing demand, substantially broadened the regional markets for LNG. It also brought new Atlantic Basin and Middle East suppliers into the trade. By the end of 2011, there were 18 LNG exporting countries and 25 LNG importing countries. The 3 biggest LNG exporters in 2011 were Qatar, Malaysia and Indonesia. The 3 biggest LNG importers in 2011 were Japan, South Korea and UK. LNG trade volumes increased from 140 MT in 2005 to 158 MT in 2006, 165 MT in 2007, 172 MT in 2008. IT was forecasted to be increased to about 200 MT in 2009, and about 300 MT in 2012. During the next several years there would be significant increase in volume of LNG trade. About 82 MTPA of new LNG supply will come to the market between 2009 and 2011. For example, about 59 MTPA of new LNG supply from 6 new plants comes to the market just in 2009, including Northwest Shelf Train 5, 4.4 MTPA Sakhalin 2, 9.6 MTPA, Yemen LNG, 6.7 MTPA, Tangguh, 7.6 MTPA, Qatargas, 15.6 MTPA, Raugas Qatar, 15.6 MTPA. In 2006, Qatar became the world's biggest exporter of LNG. As of 2012, Qatar is the source of 25% of the world's LNG exports. Investments in U.S. export facilities were increasing by 2013 such as the plant being built in Hackberry, Louisiana by Sempra Energy. These investments were spurred by increasing shale gas production in the United States and a large price differential between natural gas prices in the U.S. and those in Europe and Asia. However, general exports had not yet been authorized by the United States Department of Energy because the United States had only recently moved from an importer to self-sufficiency status. When U.S. exports are authorized, large demand for LNG in Asia was expected to mitigate price decreases due to increased supplies from the U.S. Imports, In 1964, the UK and France made the first LNG trade, buying gas from Algeria, witnessing a new era of energy. Today, only 19 countries export LNG. Compared with the crude oil market, the natural gas market is about 60% of the crude oil market, of which LNG forms a small but rapidly growing part. Much of this growth is driven by the need for clean fuel and some substitution effect due to the high price of oil. Japan, South Korea, Spain, France, Italy and Taiwan import large volumes of LNG due to their shortage of energy. In 2005, Japan imported 58.6 million tons of LNG, representing some 30% of the LNG trade around the world that year. Also in 2005, South Korea imported 22.1 million tons, and in 2004 Taiwan imported 6.8 million tons. These three major buyers purchased approximately two-thirds of the world's LNG demand. In addition, Spain imported some 8.2 mmtpa in 2006, making it the third largest importer. France also imported similar quantities as Spain. Following the Fukushima Daiichi nuclear disaster in March 2011, Japan became a major importer, accounting for one-third of the total. European LNG imports fell by 30% in 2012, and are expected to fall further by 24% in 2013, as South American and Asian importers pay more. Cargo diversion. Based on the LNG SPAs, LNG is destined for pre-agreed destinations, and diversion of that LNG is not allowed. However, if seller and buyer make a mutual agreement, then the diversion of the cargo is permitted, subject to sharing the additional profit created by such a diversion. In the European Union and some other jurisdictions, it is not permitted to apply the profit-sharing clause in LNG SPAs. Cost of LNG plants. For an extended period of time, design improvements in liquefaction plants and tankers had the effect of reducing costs. In the 1980s, the cost of building an LNG liquefaction plant cost $350 per TPA. In 2000s, it was $200 per TPA. In 2012, the costs can go as high as $1,000 per TPA, partly due to the increase in the price of steel. As recently as 2003, it was common to assume that this was a learning curve effect and would continue into the future. But this perception of steadily falling costs for LNG has been dashed in the last several years. The construction cost of Greenfield LNG projects started to skyrocket from 2004 afterward and has increased from about $400 per ton per year of capacity to $1,000 per ton per year of capacity in 2008. The main reasons for skyrocketed costs in LNG industry can be described as follows: low availability of EPC contractors as a result of extraordinary high level of ongoing petroleum projects worldwide. High raw material prices as a result of surge in demand for raw materials. Lack of skilled and experienced workforce in LNG industry. Devaluation of US dollar. The 2007–2008 global financial crisis caused a general decline in raw material and equipment prices, which somewhat lessened the construction cost of LNG plants. However, by 2012 this was more than offset by increasing demand for materials and labor for the LNG market. Small-scale liquefaction plants. Small-scale liquefaction plants are advantageous because their compact size enables the production of LNG close to the location where it will be used. This proximity decreases transportation and LNG product costs for consumers. It also avoids the additional greenhouse gas emissions generated during long transportation. The small-scale LNG plant also allows localized peak shaving to balancing the availability of natural gas during high and low periods of demand. It also makes it possible for communities without access to natural gas pipelines to install local distribution systems and have them supplied with stored LNG. LNG pricing. There are three major pricing systems in the current LNG contracts: oil indexed contract used primarily in Japan, Korea, Taiwan and China. Oil products and other energy carriers indexed contracts used primarily in continental Europe. And market indexed contracts used in the US and the UK. The formula for an indexed price is as follows: Cp equals Bp plus I squared x, Bp, constant part or base price, I squared gradient, x. Indexation. The formula has been widely used in Asian LNG SPAs, where base price refers to a term that represents various non-oil factors, but usually a constant determined by negotiation at a level which can prevent LNG prices from falling below a certain level. It thus varies regardless of oil price fluctuation. Oil parity. Oil parity is the LNG price that would be equal to that of crude oil on a barrel of oil equivalent basis. If the LNG price exceeds the price of crude oil in BOE terms, then the situation is called broken oil parity. A coefficient of 0.1724 results in full oil parity. In most cases the price of LNG is less the price of crude oil in BOE terms. In 2009, in several spot cargo deals especially in East Asia, oil parity approached the full oil parity or even exceeds oil parity. S-curve. Many formulae include an S-curve, where the price formula is different above and below a certain oil price, to dampen the impact of high oil prices on the buyer, and low oil prices on the seller. JCC and ICP. In most of the East Asian LNG contracts, price formula is indexed to a basket of crude imported to Japan called the Japan Crude Cocktail. In Indonesian LNG contracts, price formula is linked to Indonesian crude price. Brent and other energy carriers. In continental Europe, the price formula indexation does not follow the same format, and it varies from contract to contract. Brent crude price, heavy fuel oil price, light fuel oil price, gas oil price, coal price, electricity price, and in some cases, consumer and producer price indexes are the indexation elements of price formulas. Price review. Usually there exists a clause allowing parties to trigger the price revision or price reopening in LNG SPAs. In some contracts there are two options for triggering a price revision: regular and special. Regular ones are the dates that will be agreed and defined in the LNG SPAs for the purpose of price review. Quality of LNG. LNG quality is one of the most important issues in the LNG business. Any gas which does not conform to the agreed specifications in the sale and purchase agreement is regarded as a Euro-OEF specification, a Euro or a Euro-OEF quality, a Eurogas or LNG. Quality regulations serve three purposes: 1. To ensure that the gas distributed is non-corrosive and non-toxic, below the upper limits for H2S, total sulfur, CO2 and Hg content. 2. To guard against the formation of liquids or hydrates in the networks, through maximum water and hydrocarbon dew points. 3. To allow interchangeability of the gases distributed, via limits on the variation range for parameters affecting combustion, content of inert gases, calorific value, Wob index, soot index, incomplete combustion factor, yellow tip index, etc. In the case of off-spec gas or LNG, the buyer can refuse to accept the gas or LNG and the seller has to pay liquidated damages for the respective off-spec gas volumes. The quality of gas or LNG is measured at delivery point by using an instrument such as a gas chromatograph. The most important gas quality concerns involve the sulfur and mercury content and the calorific value. Due to the sensitivity of liquefaction facilities to sulfur and mercury elements, the gas being sent to the liquefaction process shall be accurately refined and tested in order to assure the minimum possible concentration of these two elements before entering the liquefaction plant, hence there is not much concern about them. However, the main concern is the heating value of gas. Usually natural gas markets can be divided in three markets in terms of heating value: Asia, where gas distributed is rich, with an GCV higher than 43 megajoules per meter 3, N, that is 1090 British thermal units SCF, the UK and the US, where distributed gas is lean, with an GCV usually lower than 42 megajoules per meter 3, N, that is 1065 British thermal units SCF, continental Europe, where the acceptable GCV range is quite wide, approximately 39 to 46 megajoules per meter 3, N, that is 990 to 1160 British thermal units SCF. There are some methods to modify the heating value of produced LNG to the desired level. For the purpose of increasing the heating value, injecting propane and butane as a solution. For the purpose of decreasing heating value, nitrogen injecting and extracting butane and propane are proved solutions. Blending with gas or LNG can be a solutions. However, all of these solutions, while theoretically viable, can be costly and logistically difficult to manage in large scale. Liquefaction technology. Currently there are 4 liquefaction processes available: C3 Mister, designed by Air Products and Chemicals, Incorporation. Cascade, designed by ConocoPhillips. Shell DMR, lined. It was expected that by the end of 2012, there will be 100 liquefaction trains on stream with total capacity of 297.2 mmtpa. The majority of these trains use either APCI or Cascade technology for the liquefaction process. The other processes, used in a small minority of some liquefaction plants, include Shell's DMR technology and the line technology. APCI technology is the most used liquefaction process in LNG plants. Out of 100 liquefaction trains on stream or under construction, 86 trains with a total capacity of 243 mmtpa have been designed based on the APCI process. Phillips Cascade process is the second most used in 10 trains with a total capacity of 36.16 mmtpa. The Shell DMR process has been used in 3 trains with total capacity of 13.9 mmtpa. And, finally, the Line Statoil process is used in the SNEH at 4.2 mmtpa single train. Floating liquefied natural gas facilities float above an offshore gas field, and produce, liquefy, store and transfer LNG at sea before carriers ship it directly to markets. The first FLNG facility is now in development by Shell, due for completion in around 2017. Storage. Modern LNG storage tanks are typically full containment type, which has a pre-stressed concrete outer wall and a high nickel steel inner tank, with extremely efficient insulation between the walls. Large tanks are low aspect ratio and cylindrical and design with a domed steel or concrete roof. Storage pressure in these tanks is very low, less than 10 kPa. Sometimes more expensive underground tanks are used for storage. Smaller quantities and less, may be stored in horizontal or vertical, vacuum-jacketed, pressure vessels. These tanks may be at pressures anywhere from less than 50 kPa to over 1,700 kPa. LNG must be kept cold to remain a liquid, independent of pressure. Despite efficient insulation, there will inevitably be some heat leakage into the LNG, resulting in vaporization of the LNG. This boil-off gas acts to keep the LNG cold. The boil-off gas is typically compressed and exported as natural gas, or it is reliquefied and returned to storage. Transportation. LNG is transported in specially designed ships with double hulls protecting the cargo systems from damage or leaks. There are several special leak test methods available to test the integrity of an LNG vessel's membrane cargo tanks. The tankers cost around $200 million each. Transportation and supply is an important aspect of the gas business, since natural gas reserves are normally quite distant from consumer markets. Natural gas has far more volume than oil to transport, and most gas is transported by pipelines. There is a natural gas pipeline network in the former Soviet Union, Europe and North America. Natural gas is less dense, even at higher pressures. Natural gas will travel much faster than oil through a high-pressure pipeline, but can transmit only about a fifth of the amount of energy per day due to the lower density. Natural gas is usually liquefied to LNG at the end of the pipeline, prior to shipping. Short LNG pipelines for use in moving product from LNG vessels to onshore storage are available. Longer pipelines, which allow vessels to offload LNG at a greater distance from port facilities, are under development. This requires pipe-in-pipe technology due to requirements for keeping the LNG cold. LNG is transported using both tanker truck, railway tanker, and purpose-built ships known as LNG carriers. LNG will be sometimes taken to cryogenic temperatures to increase the tanker capacity. The first commercial ship-to-ship transfers were undertaken in February 2007 at the Flotra facility in Skerpeflo, with 132,000 m3 of LNG being passed between the vessels Excalibur and Excelsior. Transfers have also been carried out by Exma Ship Management, the Belgian gas tanker owner in the Gulf of Mexico, which involved the transfer of LNG from a conventional LNG carrier to an LNG regasification vessel. Prior to this commercial exercise, LNG had only ever been transferred between ships on a handful of occasions as a necessity following an incident. Terminals. Liquefied natural gas is used to transport natural gas over long distances, often by sea. In most cases, LNG terminals are purpose-built ports used exclusively to export or import LNG. Refrigeration. The insulation, as efficient as it is, will not keep LNG cold enough by itself. Inevitably, heat leakage will warm and vaporize the LNG. Industry practice is to store LNG as a boiling cryogen. That is, the liquid is stored at its boiling point for the pressure at which it is stored. As the vapor boils off, heat for the phase change cools the remaining liquid. Because the insulation is very efficient, only a relatively small amount of boil-off is necessary to maintain temperature. This phenomenon is also called auto-refrigeration. Boil-off gas from land-based LNG storage tanks is usually compressed and fed to natural gas pipeline networks. Some LNG carriers use boil-off gas for fuel. Environmental concerns. Natural gas would be considered the most environmentally friendly fossil fuel, because it has the lowest CO2 emissions per unit of energy and because it is suitable for use in high-efficiency combined cycle power stations. For an equivalent amount of heat, burning natural gas produces about 30% less carbon dioxide than burning petroleum and about 45% less than burning coal. On a per-kilometer transported basis, emissions from LNG are lower than piped natural gas, which is a particular issue in Europe, where significant amounts of gas are piped several thousand kilometers from Russia. However, emissions from natural gas transported as LNG are higher than for natural gas produced locally to the point of combustion, as emissions associated with transport are lower for the latter. However, on the west coast of the United States, where up to 3 new LNG importation terminals have been proposed, environmental groups, such as Pacific Environment, Ratepayers for Affordable Clean Energy, and Rising Tide have moved to oppose them. They claim that, while natural gas power plants emit approximately half the carbon dioxide of an equivalent coal power plant, the natural gas combustion required to produce and transport LNG to the plants adds 20 to 40% more carbon dioxide than burning natural gas alone. Safety and accidents. Natural gas is a fuel and a combustible substance. To ensure safe and reliable operation, particular measures are taken in the design, construction and operation of LNG facilities. In its liquid state, LNG is not explosive and cannot burn. For LNG to burn, it must first vaporize, then mix with air in the proper proportions, and then be ignited. In the case of a leak, LNG vaporizes rapidly, turning into a gas, and mixing with air. If this mixture is within the flammable range, there is risk of ignition which would create fire and thermal radiation hazards. Gas venting from vehicles powered by LNG may create a flammability hazard if parked indoors for longer than a week. Additionally, due to its low temperature, refueling an LNG-powered vehicle requires training to avoid the risk of frostbite. LNG tankers have sailed over 100 million miles without a shipboard death or even a major accident. Several on-site accidents involving or related to LNG are listed below. 1944, October 20. The East Ohio Natural Gas Company experienced a failure of an LNG tank in Cleveland, Ohio. 128 people perished in the explosion and fire. The tank did not have a dike retaining wall, and it was made during World War II, when metal rationing was very strict. The steel of the tank was made with an extremely low amount of nickel, which meant the tank was brittle when exposed to the cryogenic nature of LNG. The tank ruptured, spilling LNG into the city sewer system. the LNG vaporized and turned into gas, which exploded and burned. 1979, October 6, Lusby, Maryland, at the Cove Point LNG facility a pump seal failed, releasing natural gas vapors, which entered and settled in an electrical conduit. A worker switched off a circuit breaker, which ignited the gas vapors. The resulting explosion killed a worker, severely injured another and caused heavy damage to the building. A safety analysis was not required at the time, and none was performed during the planning, design or construction of the facility. National fire codes were changed as a result of the accident. 2004, January 19, Skikda, Algeria. Explosion at Sonatrach LNG liquefaction facility. 27 killed, 56 injured, 3 LNG trains destroyed, a marine berth was damaged and 2004 production was down 76% for the year. Total loss was $900 million. A steam boiler that was part of an LNG liquefaction train exploded, triggering a massive hydrocarbon gas explosion. The explosion occurred where propane and ethane refrigeration storage were located. Site distribution of the units caused a domino effect of explosions. It remains unclear if LNG or LNG vapor, or other hydrocarbon gases forming part of the liquefaction process initiated the explosions. One report, of the U.S. government team site inspection of the Sonatrach Skikda LNG plant in Skikda, Algeria, March 12, 16, 2004, has cited it was a leak of hydrocarbons from the refrigerant process system. See also, references. Other sources.